Thank you. I don't see our speaker yet. I have just sent an email to him. I hope everything is fine at his side. It is Daniel Gruss from TU Graz. He has a starting grant in sustainable security, so he's really a security expert, well known from the Meltdown and Spectre kind of discoveries, which made their way into media a couple of years ago. He was also doing his PhD in this area, and has now an ERC starting grant. It's the highest European basic research grant in sustainable security. So I have introduced him, and as I said, I sent him an email. I hope that he will still join us. We just wait a couple of minutes. Yeah. There is Daniel, looking like like Daniel Gruss. Great, Daniel, to have you.
Okay.
And I have already introduced you. So you should be able to share your slides.
Yes, can you understand me well? Does it work? Or I can also try the other microphone. Maybe that one is better. Does that work?
This is, at least for me, it's better.
Okay, sounds good. Yeah, very good. Yeah, sorry for the delay. I'm not used to this streaming setup anymore, and I couldn't get it to work. So I was just sitting an hour here and trying to get this to work, and now I'm like, okay, I just have the PDF, and I'm trying to share it just like that.
Great. I
won't
did
have-
the introduction already. Last year you were the first, and with your presentation last year, I really kept saying it's so exciting what you present about energy savings and possibilities we have, so I don't have to read any thriller anymore. So I'm looking forward to your presentation, and it's your floor.
Thank you.
Oh.
All right. Does this work?
Yes.
Yes. Unfortunately, I don't have my regular streaming setup. Usually I would be walking around in the slide, but I couldn't get it to work now. That's it now. Security. Can we afford to have it? Can we afford not to have it? It's a tough question. The problem that I see here is that if we think about security, a lot of security people, maybe a lot of you are not from the security community. A lot of security people feel like if you have a discussion about security that, that's not optional. Security, you can't make this optional, right? And then there's a stark contrast. If you go outside of the security community, people are like, well, but it's not that important, right? So while in the security community, people would say, oh, your mitigation only has an overhead of 10%, that's good. Outside of the security community, people are like, well, it has an overhead of 0.05%, that's too expensive. And this is a stark contrast, and we have to discuss how we can move forward from here and what the overall problem in terms of security is. A lot of the research that I'm presenting today is done by my PhD students, and my research group was, of course, funded by several projects, including the SpyCode cluster. That is a cluster together with TU Wien and several other universities in Austria. And the first thing that I want to discuss with you is side channel. What is a side channel? A side channel, that's my definition of a side channel, is obtaining metadata and deriving secrets from it. So let's figure out what a side channel is in terms of concrete examples. For instance, profiling the cache utilization with performance counters. Is that a side channel? Well, are we getting metadata? Yeah, the cache utilization is metadata. Are we deriving actual data from it? Not really. So in this case, not a side channel. Observing cache utilization with performance counters and using it to infer a crypto key, well, yes, then it becomes a side channel. Similar, you might have heard, if not, it's not a problem, you might have heard about flush and reload. And people say, oh yeah, it's a flush and reload side channel attack. But is flush and reload really a side channel? the question is what you're doing with it. If you're just measuring memory access latency, that's metadata, but you're not deriving anything from it. You're not inferring anything. So it's not a sidechain. As soon as you start inferring something, for instance, keystroke timing or cryptographic keys, as soon as you do that, then it becomes a sidechain. All right. One thing that we learned over the years was that in several cases where we thought, oh yeah, it's a sidechain, it has a lot of noise because it's metadata. And if you think about it mathematically, what we have there is an implication arrow, basically. So we are saying we have data that implies this type of metadata or this effect on the metadata. But what we are doing is basically we are writing this arrow backwards, the implication backwards. And the mathematicians that I talk with, all if I tell them what we do, they all go like, do that, right? But we can if we take these additional assumptions like, okay, but we have some control over the system, and yeah, there's some noise. There will be some cases where it doesn't work. And very often we thought, oh, so we have this new attack, this new side channel, but there's a lot of noise. And turns out in almost every case where we observed noise, we later on discovered, or others later on discovered, that it was not noise. It was just data that we didn't know how to interpret yet. And if you think about it, your computer is built by humans. Everything in your computer will be completely deterministic, except for maybe the randomness source. But everything that it's supposed to do, basically everything, is completely deterministic. How can there be noise in something like cache timings? This should be completely deterministic. And it is. It is. And that means there is no noise. Noise is just data that we don't yet know how to interpret. You build a new feature, you have a new timing difference. Congratulations, you expose that variable in terms of timing differences to an attacker. Great. Let's take a look at these timing differences in more detail. And one example that I want to talk about here is the flush and reload attack and then meltdown. And these are based on out-of-order execution. Out-of-order execution is a mechanism that is responsible for a lot of the performance gains that we've seen in the past 2 decades when we first had out-of-order execution processors. By now, if you would disable out-of-order execution, you would go back to the performance of maybe a Raspberry Pi or something, a second edition Raspberry Pi or something. So we can't do that. We would really lose very, very much performance, especially for the larger systems. And for the smaller systems, we would lose efficiency as well. So what do we do? Out-of-order execution works pretty much like cooking. When we cook, we take the recipe, but we don't necessarily follow all the steps of the recipe in order. So what we do, when I cook, I first start with the ingredient list and put all the ingredients on the table. I realize, oh, it's not there. So I have to go to the supermarket, get this. And then this happens to me 3-4 times. Then I have everything at home, right? But I went to the supermarket back and forth 3-4 times. This takes time. So I talked about this with my colleagues in the office, and these are clever people, and they proposed this thing to me that I think is very ingenious. It's food cache. In this, you can store food and you save time because you don't have to walk to the supermarket all the time, to the grocery store all the time. Instead, you can keep the food at home. And if you want to cook something, very good. You don't have to worry about this. So the food cache. Turns out this already exists. Not in the real world, of course, but inside computers. Computers have such caches. And what they do is basically, they just move this one over here. Yeah, that's better. Very good. What they do is they take, when you load data, the first time it's a cache miss, so they have to walk to the supermarket, well, or the DRAM in this case, and then they get the response, and then they store it there. The nice part about data is that data doesn't it doesn't go bad as much as food, right? And if you consume it, you can consume it again. We all know this thing about data theft, where the data is still there, right? Yeah. So the second time we access it, it will be a cache hit because it's already in the cache, so we can access it much faster. First time DRAM access, so it's slow. Second time no DRAM access, much faster. And with this, we can build our first attack because we have a timing difference. It depends on something. This is a deterministic machine. We can exploit it. Every timing difference that you introduce into a system can and will be exploited. So how do we exploit this? Let's assume we have shared memory. Then cache lines that are in shared memory will be cached either for both or for none of the two processes. Here, an attacker and the victim process. And the attacker can flush this memory because it's its own memory, right? So why wouldn't it be allowed to flush it? Flushes it from the cache, the victim accesses it afterwards, depending on a secret bit. If it's 1, it's accessing this location. If it's 0, it's not accessing this location. And then maybe it's in the cache again. And the attacker then can access this location again, measure how long it takes, and it will be fast if the victim accesses the data, slow otherwise. So the attacker learned the secret information. So we have timings just plotted here to illustrate how easy this is, because I'm not good at mathematics. We already talked about that part. But if you take a look at these histograms, you only put a threshold there at maybe 180, 190, and you're done, right? No complicated mathematics needed. But some distributions look a bit more ugly, and there you will need some more clever statistics to distinguish the two distributions. All right. Yeah, I have a demo prepared. I hope the video works. Does it work? Yeah. Okay. So what we can see here is I'm scanning over a shared library. This is libgedit. Any user can open this library without permissions. And I'm measuring the number of caches that I get on these addresses while typing in the editor. Now I'm taking just a random line here, which has 24 cache hits while I was typing, right? And now I can see every time that I press a key, I get the exact timing on the other side, on the terminal, without any permissions. Any guest user on your system can do that. Great. This still works on current systems. This never was mitigated. Why is this dangerous? Maybe some of you are using these swipe keyboards, and a lot of information of the swipe keyboards, where you swipe from one key to the other, is the timing between the points where you turn around the finger. A lot of information is already conveyed in that. And if you just take this information, train the same neural networks with that, then they will still be able to predict what you entered. Great. And the same thing is true for your regular keyboard, because also there your fingers travel. And so machine learning system can learn which letters you were typing. Sometimes that's not even necessary, because we found out that actually some locations leak specifically the key that you were typing. For instance, you can see here on this library, in this library version at address 7C800, only key N accesses this memory location. If I press something else, then this cache line doesn't see any cache activity. What does that mean in terms of security? Well, if your password contains ends, I know where they are and how many, and so you shouldn't use ends in password. No, that's not, no, you can. Yes. Okay, let's go from this one. This is a simple cache attack. This is like leaking metadata, timing it, the cache status, for instance. In this case, was there a cache hit on this address or not? If there was a cache hit, I know which secret, or I infer what secret it might have been. There could have been a spurious cache hit on this address for some reason. There could be someone else just loading the library for some reason. So there could be many reasons why I'm seeing a cache hit on this address. But because I'm making these additional assumptions of what is going on, maybe even controlling the system to some extent, I'm allowed to write the implication backwards. So this is what we're doing here. Now let's go one step further and go from side channels to actual data linkage. That's not a side channel anymore, but we will still use side channels. More specifically, we will use the side channel as a layer of indirection. So what do we do here? This is Meltdown attack, actually just the first of the two lines, where we take a kernel address and we try to read from this address. So we take the kernel address, we cast it to a character pointer, dereference it, and then we load 1 byte of kernel data into this character. Of course, this shouldn't work. So everyone here who attended an operating systems class already knows this is not supposed to work. If you try that, you will get a seg fault. And I'm fully aware of that, and I will get a seg fault, and I'm fine with that because I just installed a seg fault handler or do this in a child process, and I don't care if the child process dies, right? So I will just access this location. What else will I do? I will execute the second line after this first line because we're running into out of order execution. And that means we don't have a problem with executing the second line, but all the results will be unrolled, and instead, of course, we get the seg fault. The second line, however, does a memory access into an array. And this array is my own array. And we're using, you can see this here, the data. We're using this secret value as an index. And if we do that, we can check whether any part of the array is cached with flush and reload like before. And if we do that, then we see what the value for data was. This is how Meltdown works. It's just 2 lines of code and we're done. Permission check is not fast enough. That's of course bad. Here you can see Meltdown. This is on a Samsung phone. We're leaking the entire kernel. This is also something that a lot of people overlooked. Meltdown did not just affect Intel. It did not just affect Intel mainly. It did not just affect Intel. It affected also Apple and some Samsung phones and some Qualcomm devices, and also an ARM chip that fortunately was not released yet, original ARM design. Then anyone else? Oh, that's pretty much it. Yeah, so iPhones were also affected by Meltdown. All right, are we going through the long Meltdown exploit? I'm not sure we have to, but maybe. So let me just skip a bit ahead. Here we're breaking VeraCrypt, the follow-up project to TrueCrypt. And this is using some disk encryption, so you won't be able to crack this container open. Okay, so we are not sudo, so we can't access this. And now this is a full end-to-end Meltdown exploit. So we will run now a Python script which uses Meltdown several times. First, to break kernel ASLR, to find where the kernel is in the address space, and then to that's the first part. Then to read from physical memory, then to search for the task struct, to search for the right process, to get to the value for the CR3 register, and then use the virtual address within that process and the CR3 register to manually do the memory lookup through the identity mapping. Then decrypt the disk image, and that is what we got here, a secret video and a credit card pin. So I would ask everyone, because I'm showing this in a demo now, my credit card pin. So please look away while I'm showing this. Okay, and then there's also a secret video. I'm not even sure I want to, oh no, okay, I will continue. Okay, so what can we do against Meltdown? And this is where we go into the direction of sustainability. We came up with a patch against Meltdown even before we discovered Meltdown. This was actually about a year earlier where we had this idea that we could do this. And we chose the name Kaiser, like the Kaiser penguin, which makes the Linux penguin stronger, right? It makes Linux better and stronger. And we said Kaiser stands for kernel address isolation to have side channels efficiently removed. So I'm not sure. So we also had other acronyms before, but we in the end we chose this one because it was compatible with the Linux penguin. Also, since all the or most of the people that were working on this were from Austria, it's also there's some connection there, right? All right. Yes, Kaiser. How does Kaiser work? Before, we had a shared address space between user and kernel. Now with Kaiser, we split this up. And that means that we have 2 address spaces, and you can already see where the overhead of this mitigation comes from. Now, when we have a context switch, we also additionally to the context switch We have to switch the address space. And that means additional time, additional memory accesses, additional energy consumed. So this can be expensive. All right. Before we talk more about the energy consumption itself, let's maybe go through Spectre as well, and then we will go through the energy consumption of this. But of course, this is not for free. Everything we do costs something, so we have to figure out how we can do this in an efficient way. So for Spectre, I will go back to when I was still a PhD student or postdoc. There was a pizza place close to our university. Unfortunately, we don't go there very often anymore. They changed owners. But back then it was really nice because they knew us and we were going there almost every day. And we were calling them and reserving a table for our group, basically. Yeah, and they already knew us. They knew, okay, so one person would, or maybe a few people would get random pizzas, not predictable. But the best pizza there was the Pizza Diavolo. So there was at least half of the people were getting Pizza Diavolo every day. Crazy, right? Every day. And so they already knew when we were calling, it's those Theo Graz guys again. Oh no. So we can already start cooking. I don't know what they ordered today, but at least half of it will be Diavolo. And this is actually what they did, speculative cooking. And we also saw that the pizza then arrived much earlier for us if we ordered Diavolo than if we ordered the other pizza, because they couldn't predict that. So they started cooking before we even ordered. So how does this work now? You want to exploit this. We're talking about security. We want to figure out why we need these expensive mitigations. So what can you exploit here? Of course, you could call them and say, table for 6, please, here's Theo Graz. And they would believe you because they don't recognize that it's not my voice, right? And then they start making the pizza, and then you show up and they are like, oh, that's not Theo Graz people. And we are a privacy conscious company. We will throw the pizza away, right? That's also what the computer would do. But the smell still lingers in the air, the metadata. Right? The data is gone, but the metadata is still there. And this is what we do with Spectre. So we have our interface. We tell the processor, we're for sure always in bounds. In this simple Spectre illustration, we're always in bounds until we're not anymore. So now index is 4. But the processor doesn't know that. The processor believes, they always speculated in that direction. It was fine. So it will still speculate in this direction and now perform a memory access that leaks the secret behind this data array. So we need to mitigate this as well because we can leak again memory from other security contexts with that. Just to give you an additional illustration of how this works. In principle, this is out of order execution. You have the operations lined up here, one after the other. There might be a prediction. And then if you predict the control flow or the, it's a bit weird here. Just check. Yeah, it's maybe better. Okay. The operations lined up here, and at the end, they always retire. So you have a prediction of the control flow or data flow in the middle, and then operations that follow after that. So the beginning is still architectural execution. Then there comes a part which we will or might unroll. We call this transient execution because it will only be there transiently for a short time, and then it will be undone, will be reverted. Now with Meltdown, it works like this, that we have an exception here, something like a fault, a seg fault, for instance, and then the data is not thrown away as it should be, like here, but instead it's passed on to the dependent operations. And that is a problem. So then we have the data in the dependent operations. For Spectre, there are tons of different variants. I just showed you one single variant, one very simple case, and that was in place, same address space with a direct conditional branch. But there are many more variants with indirect branches, with returns, with stores that are skipped, with branches that are completely ignored. There is the possibility to train all these Spectre variants or to exploit these Spectre variants from different origins and in different contexts. So there are many, many Spectre variants, and all of them need mitigations. And if you just look at the Meltdown and Spectre and maybe a few follow-up works, the mitigations against those, the initial recommendation by Intel was to have at least IBRS, STIBP, and IBPP. And these have significant performance overheads. This is really significant, right? If you just take a look at Kaiser alone, this is already 0 to 2.6% of performance less. This is just a single patch. So this is really significant. All right. But before we go for the actual performance and energy discussion, let's maybe talk a bit about some other attack, and then we will talk about the performance losses. So for this one, this was from a TV show from 2018. This guy just got shot after he discovered there was a rowhammer attack going on a satellite. I was like surprised that they have this in a TV show, because rowhammer was actually what I was working on in 2014, 2015, also since then several times. This is from 2015. I gave a talk at the Chaos Communication Congress there in front of about 3,000 people. And that was at the end of the first year of my, or beginning of second year of my PhD. That was fun. And what we did was we mounted a rowhammer attack from the browser, which you can see here. We have an HTML file, we're running JavaScript, and we are actually modifying memory without accessing it, inducing bit flips. This is, of course, a problem. So let's figure out how this works. So in DRAM, initially we already, so one of the first slides, we already had the DRAM there, right? We have the cache and then the DRAM, we access the memory from there. Typically, you will have gigabytes of DRAM. In there will be small cells, capacitors, resistors, and they they store the actual data. And when you want to access any data from these cells, from these capacitors, then you have to copy this into the row buffer, which is kind of a, it's a different structure. It can vary, but depending on how it's implemented. In some cases, it's just a run-through wire feedback loop. In other cases, it might even be an SRAM array. So what we do here is we activate the row. The memory controller sends this signal, this command to the DRAM module, and the DRAM module activates this row. All the bits run through into the row buffer, and then you can read them from the row buffer. They are sent to the CPU. Now, if I want to read a different memory location, I have to activate a different row. Now, these cells are capacitors with resistors, with transistors in front of them, capacitors, and they discharge over time. Capacitors always lose charge over time, even if you don't do anything, right? So another effect that occurs here is some crosstalk across these wirings where electrons tunnel through the substrate, and actually you have additional leakage then, and this depends on what is going on in a neighboring cell. So if you're discharging a neighboring cell, some electrons tunnel through, and that means they leak faster than other cells that are further away. That means rowhammer increases this leakage if there are excesses in close proximity. So that means you have to recharge the cells also all the time continuously, because they discharge by itself, but also rowhammer increases this problem, and we will talk a bit about rowhammer and the mitigations soon. Yeah, so in this case, if we access those two rows often enough, we get bit flips in the middle row. Different rowhammer variants that have been proposed initially were, for instance, single-sided hammering, where you just hammer random locations in your DRAM bank and then see some bit flips next to one of them. Double-sided hammering, where you sandwich a row and see bit flips in the middle. But then what we discovered in 2018 was that you can't just hammer 2 rows or a single row like before, but it's also possible to focus on just one row in the bank and not hammer any other rows and just hammer this one. And then we also saw bit flips next to it. More recently, in our work together with Google, we discovered that a mitigation called TRR, which is supposed to mitigate the row hammer problem by refreshing neighboring rows, actually can also be abused to induce row hammer bit flips, because we activate these outer rows now. TRR will activate the inner rows from time to time to refresh those rows, but this is actually enough to induce bit flips in the middle. Oh no, not another row hammer attack. So how well does this work? Let's see, this is the one location row hammer attack that we can see here, and we just hammer for a few, this is real time, we're just hammering for a few seconds and we see tons of bit flips already. And what does bit flip mean? Let's figure out what this means for security. For instance, in the pseudo binary, you will find a jump equal instruction, and this one jumps if the password is correct. So what we want to have is now we want to invert the logic in a way. So let's see what happens with a single bit flip. This is all not so useful. Maybe. Oh, jump not equal. Great. If we flip this bit, then anyone who enters a correct password will be logged out. But with the wrong password, you're logged in. Great. So let's talk a bit more about attacks. I will be done in a second, but maybe something that I want to talk about with you. Yes. Yes, exactly. That is the plunder vault attack. Yes. Okay. I will actually just skip a few slides because I think I have them I have duplicated because I have made a last minute update to my slide deck. And now I don't want to do that here, but I want to skip here first. So let's talk about the security costs of Meltdown and Spectre. If you think about the security costs for Meltdown and Spectre, for instance, for the Chrome browser, initially you had the Chrome browser, also Firefox, running just one process. And you might have seen that more recently, they are running one process per tab or per security context. And this has an overhead. This has an overhead of actually 8.2%, according to the published literature on this. So this is really a lot, 8.2% of performance overhead. And performance overhead, in the most general case, translates to energy overhead. Pretty bad. For Meltdown and the Kaiser mitigation, we estimated back then plus 5%, but it depends a lot on the use case. Now the question is, and can we afford this? If we think about the energy consumption of our global ICT, we see that currently we are at around 12% of global electricity, and we will reach more than 21% by 2030. This estimate is a bit older. This is from 2018, and this was before the largest Bitcoin bubble, and this was also before the AI bubble. So the estimate by now is much, much higher. So probably beyond 25%. It might even be beyond 30% of global electricity. And this is something you have to really think about for a moment. Electricity, all the electricity that mankind produces in a year, 30% of that just for our computers. That's a crazy number. That's really crazy if you think about all the other stuff that runs on electricity. Yeah, it looks a bit like an exponential growth curve. It's unfortunate, right? Exponential growth in energy demand, not very good. Let's talk about the actual cost of Meltdown and Spectre in this case. And I will focus just on the Meltdown patch here, just the Kaiser patch. And I made the ballpark estimate. I took the 5% of overhead. And I said, well, this applied to pretty much every computer out there. So let's just apply this to every computer, all the energy consumption that we have. What do we get? In 2018, 7% of electricity was consumed by our global ICT, less than 2% of greenhouse gas emissions. And that means a meltdown patch in 2018 was, in the worst case, something like plus 0.09% in greenhouse gas emissions. That's not zero, right? So that's a single patch, and we are already close to, let's say, 0.1%. Maybe it looks much better in practice because not all machines need a patch against this. Maybe we are at 0.05%. Maybe we are even at 0.01%. But this is not nothing, right? This is still a considerable amount that we have to think about. So let's maybe then take a look at 2030, a single patch. Let's see how affordable our current approach to security is with these patches and overheads. How much overhead does it have in 2030? 0.4% if we assume 25% of energy is consumed by global ICT. 0.4%. That's, well, you can have the choice, either 3 security patches for everyone or global air traffic. Make a choice, right? It's an easy choice. People will choose the air traffic. Right. There are alternatives, though, to security, right? We don't need security, and this is something that is already happening. If you take all the costs, the CO2 price into account, it might be cheaper to just abandon security completely and focus on insurance companies instead. Oh, you got hacked. Here are $1,000 payout from your insurance, and then next time, take care. And next time it will only be $500. But please keep paying your premiums. Yes. So there are alternatives. We talked about the cost of security, but then again, we didn't even answer the question of how expensive security is. And actually, we don't know. If you think about the CO2 costs of security, even the performance costs of security, this is very difficult to measure. And if you take a look at the energy efficiency, I looked at almost 500 papers from 1 year in the top 4 security conferences. Only two papers provide energy costs. We don't know how expensive security is because we don't measure it. Very easy, right? We don't know I don't know how much I weigh until I go and weigh myself, right? No problem. So how valuable is security? That's the other question, right? How do we measure how valuable security is? And that's also very difficult because if we make a system more secure, how much more secure is it? 3, 4, 37? We can't measure it. There's no scale to that. There is no 100% security. You can never have a system which is 100% secure. You also can't have a system which is 0% secure. It just doesn't make sense to measure it. Right? So it's not clear how expensive it is. It's not clear how valuable it is. And then some folks in the more systematic part of security research then argue, well, is security research even a research field? Because it doesn't sound very systematic. It doesn't sound very scientific. But I think there are scientific parts to it. Yeah, also, why the security community? I get this question a lot when I lobby for more action on energy efficiency in the security community. And people are like, no. Like, first of all, those people running those generative AI models, they should save energy. Yes. And then the Bitcoin community. And no, not us. Also, you can't just, security is too important. I made this poll actually in a security context. So I gave a talk to a lot of security researchers, and at the beginning of the talk, I asked them, okay, so who would advise to install the Meltdown and Spectre patches? And all the hands went up. Everyone said, yes, this should be installed. And then I asked this question. This was a room full of security experts. At the end of my talk, who would advise to install the Meltdown and Spectre patches in 2030 should a vulnerability like this come up again? And almost no hands went up. And I was asking them, you are the security experts. If you don't even believe that we should be doing this, then why are we still doing it? So we need to figure out how we make security more sustainable. Yeah, just ignore the problem. Yeah. Moore's law is not going to save us because Moore's law is dying. It has been for several years. Initially, they said, well, the transistor count or the computational power that we have per energy unit translates pretty much to the same. Doubles every 12 months, then they went down to 18 months, then they went down to 24 months. Now it's not even clear whether we can make it double in 3 years. And it will go slower and slower. So the end of Moore's law is already here. Now let's go for something more positive. So we have to, I showed you all the problems now, lots of security problems. All of the security problems cost energy and performance when we patch them. So what can we do against that? How could we gain anything positive out of it? Should we just turn off the internet and be done with it? Maybe. I'm not saying no, but maybe there are other solutions as well. So one thing that I've been doing on my computer since the early 2000s was undervolting. Let me first stay on this slide for a second. When I had there was an old HP laptop and it was overheating all the time. So if I wouldn't undervolt it, it would just shut down. Now, undervolting is great because you leave the frequency basically the same, and the voltage, you reduce that one. So if you take a look at a performance benchmark here, what actually happens when you undervolt the system, you get more performance out. I screenshotted this just from a random YouTube video on undervolting. You get more performance if you undervolt your CPU. Why is that? Because the CPU today, if you take a look at your CPU, there will be something called the TDP, the thermal, what was it called? Thermal dispense power or something, which basically defines the power limit. It defines how much power the CPU may consume in a certain time frame or in one moment, depending on which limit you're looking at. And this one defines the performance of your CPU. Even if you buy identical CPUs, they might run at different voltages, so that you can have a performance difference of 20–30% with identical CPU models just because one runs at a lower voltage. So lower voltage means that it takes a longer time until it reaches these energy limits, these thermal and energy limits. And that means it can clock higher for a longer time and then gain a higher performance. And you can do the same on your computer. You can just undervolt your computer and then get free performance out of it. Great. I actually did this to my system as well. On my laptop that I have this one here, when I got this laptop, I had 13 hours of battery runtime on Linux. When I undervolted it, 23 hours of battery runtime on Linux. Great. So I had something like 20 to 30 or even 40% more battery runtime for most of the last decade. So that was for free. Great. And if I ran my systems totally fine like that for 10 years or more, why do we actually waste 40% of the energy? And then it's like, no, not another security problem, like Plundervault. Okay. Yes. I won't go too much into the details of Plundervault. I can show you basically this one here. So we have an endless loop. You can see this here. There's an endless loop with always computing the same value, dead beef times the multiplier. It should never break out of the loop. But if you undervolt the system, let's do that. Yeah, this is how we undervolt. Here we are undervolting, minus 256. And what happens? Well, at minus 259, we have a bit flip. Great. What can we do with bit flips? We already know what we can do with bit flips. Yes, and also here we can see how far can we undervolt this. We can undervolt this pretty much to this, only 2/3 of the voltage. So this is a significant amount that we undervolt here. All right, let me just, this is also a curve where we can see how far we can undervolt. Let me just move on. So why are problems like Rowhammer or Plundervolt still there? Why are they not solved? Exploitability has been described in 2014 of Rowhammer and Plundervolt in 2020. How incapable are we even, right? So the problem is misunderstandings. These create bad incentives. If you take a look at the security community, how we do security, or the cryptography community, how they do security, it's usually something where they say, well, let's assume the attacker can change all the data. How can we still have security guarantees if they can change all the data? For instance, by having a digital signature. For our computer architecture, we don't do that. And the people designing this are also not trained in security to the same extent as some of us are. So what are we doing? Well, for DRAM, typically we say, oh, well, how many bit flips will actually occur? Just add a bit more reliability. For instance, 1 bit in 64 bits can be corrected, or in DDR5, 1 bit in 32 bits can be corrected. If more flip, that won't happen, right? So this is what we do. And actually, this has a problem because we assume what is still reliable. And as soon as an attacker can bypass this, we have a problem. Yeah. Yes. Exactly. Exactly. We're not really changing the game. The attacker doesn't care whether we have ECC memory in there or regular memory, totally doesn't care about this. 1 bit flip too much is 1 bit flip too much, whether we have ECC or not. And this is also what we observed with vendors, for instance, Apple and Google, they all use ECC memory now in their smartphones, but still Rowhammer attacks are possible. Oh no, a new Rowhammer attack. Yeah. So yes, this is what they did. It's an optimization problem. We never know how far is still safe. And this can also change over time because the adversaries learn and they can adjust to what you do to mitigate these attacks. The problem that we're seeing here is that we are discussing security versus reliability. And when I started my PhD, people always told me, security is so you have a pyramid and then there's like, at the bottom, there's the basic functionality, then at some point reliability, then further functionality and so on and so on. And at the top of the pyramid, there is the security, right? This is the thing that you add at the very end on top of it. I think this is fundamentally wrong. Why do I think this is fundamentally wrong? Because reliability, the basic assumption there is what is normal operating conditions? Which operating conditions are still normal? And something, when I talk to people from the reliability community, something that I get very often is that I say, well, but what if the attacker does this and this? And they're like, well, we are assuming a normal scenario, no adversary. My impression is in the last 2.5 decades, or even 3 decades, we eliminated this threat model entirely because all of our systems are connected to the internet. There's always an adversary. The threat model where you say, oh, let's assume there is no adversary doesn't make sense anymore today. So we always need security and we can never say, oh, we just need reliability. And I would say we might even have to replace reliability completely with security. And then people tell me, oh no, that's not nice. I got actually projects rejected where I think someone was really angry because I basically wrote in a project proposal that we shouldn't be doing reliability measures anymore here and there, but replace this completely with security. And they were like, no, you're stealing our jobs. So I don't know. Yeah. So I want to even go further. I want to use security for efficiency. And I also did this. I proposed this to Intel. I had a very nice idea there that I will talk about next. And this was also rejected. And Intel said this was I'm almost literally quoting a review for the project proposal here, where they said, do you really think you can do this better than our well-established solutions that we have since decades? If anyone ever tells you this, then please keep poking, because you don't know how many people were shut down before you with the same argument. Very likely many, because you will not be the first person to hear this. And very likely there's something to find there, because a lot of creative, clever minds have been shut down before, and you will not be the first that gets this response. So what we want to do is we want to make sure that that bit flips only degrade performance, but they do not impact security. So how do we do that? We, instead of the error correcting code that we have in our modern DRAM, which occupies something like 12.5 to 25% of the chip area on the DRAM, we introduce a cryptographic MAC in exactly the same size. The cryptographic MAC, that's a nice part of cryptography, can detect any number of bit flips with cryptographic guarantees. But the problem then that we saw is, how do we correct this? So the most naive approach for this was to just use a brute force search. So we just brute force search for correct data. And if we do that, then we see that actually the correction duration is not that high. So we can then see, okay, for the case of a single bit error, we are in the same order of magnitude as a ECC RAM. For 2 errors, which ECC RAM usually can't do anymore, we are still in microseconds, and still up to 6 errors, we can still do a correction in a reasonable time frame. One further advantage is that this is only a per thread issue. So if one thread gets a correction fault, the other threads can still continue working on their memory. So everything is fine there. So it has a lot of advantages over the basic ECC design. Yeah, security guarantees pretty high. So silent data corruption less than 1 per 10 to the 9 billion years. This is just the property of the cryptographic algorithm, multiplied by the probability of a row hammer bit flip. Second pre-image after hammering for 1 year straight is extremely small. If we have 8-bit errors, of course, if we have very many errors, then there is a chance that we correct incorrectly. But the question is whether you should even correct up to 6 or 7 or 8-bit errors. There is a limit where you should say, stop, we don't correct this one. Or you use a larger code. For instance, for DDR5, the numbers look even better than this. This is for DDR4. Yeah, there was also, if you want to take a look there on YouTube, there is a trailer for CSI Rowhammer. Please check this out. It also explains the paper in a very short moment. And you can see the first author here on the right, that's Jonas Juffinger. Yes, yeah, we did this. This is in principle how this is implemented. Yeah, and we have the security guarantees. Yes. Performance overhead. This has a performance overhead, but it also has the potential to save a lot of energy, but it's not immediately visible here. But we are saving a lot of energy by reducing the refreshes, for instance. The vendors are already doing that, but they just have the security problems now that they haven't taken into account yet. If you do that, you can optimize systems, of course, way more aggressively, because there's nothing to worry about. Actually, a system which has a bit flip every now and then might be way better in terms of performance and efficiency than the other way around. I'm just taking a look at the time. How much time do I still have left? 2-3 minutes? Okay. Then I will make it very short for the last part. So I talked a bit about this undervolting part and the efficiency we can gain with that, right? Can we make this as secure as well? And there we designed also a system how we can do that. And I will jump right into that. So we have both a hardware extension and a software extension where we disable some opcodes and then switch curves. And the essence of this is basically that we introduce an efficient DVFS curve, an efficient voltage frequency curve, and the conservative one is that we are using today. And we will switch these curves then in an efficient way so that we can actually operate most of the time on the efficient curve, and only for some operations have to switch back to the blue and conservative curve. Just more illustrations of how this works, but I will just skip through that. Efficiency gains, performance and efficiency gains. We can see this here. Actually, we did this. We measured this on real processors, and there we can see the energy efficiency for some systems goes up by 20% and more. And this is for free on current systems just by applying our security measure. By disabling some opcodes that are not so secure, then running at a lower voltage most of the time, increasing the voltage only for those opcodes who really need that. A lot of performance gain and efficiency gain. Here's also a bigger table of how much efficiency we gain. There are some extreme cases, but overall we can see here 20% is very easily possible. So the conclusion, we have decade-old problems like Rowhammer that can be solved with principal security. We can solve them, and adding security here can increase efficiency. We saw this now with this last example, but also for Rowhammer, this effectively increases the efficiency because you can optimize more aggressively. And this is a new and unexplored area that needs a lot more research, and I'm trying to convince more and more people to actually do something in that direction. And I hope that in a few years, we are not talking about getting rid of security anymore, because security has just taken the place of reliability, and we can't get rid of it anymore because otherwise our systems don't work. Thank you for your attention.
Thank you very much, Daniel. Very inspiring. A lot of interesting ideas. The floor is open for a couple of questions if there are one. There was a question about how much additional memory does this need, and another colleague I think already answered the question in the chat.
That's true. That's right. So for CSI Rowhammer, that's a drop-in replacement for ECC. So it has exactly the same memory overhead. That's true.
Okay. I don't know if there are further questions from the audience. One question I would have is, one more general question. You were saying that the awareness for energy costs of security was just, you were looking for the papers and you said 2 papers out of hundreds. I think this is one of the reasons why we have this lecture, that I guess that still we, as computer scientists, we should pay more attention to all,
Exactly,
the problems we cause, so to speak.
Yes.
There was an interview with Ivona Brandic just recently, where she stated that, like this blockchain technology, I don't want to bash on it, but it will use more and more energy, and it will use in a couple of years the energy of Argentina. I think like that. One thing, I would have another question going more, post-quantum security. This is a total different area, but of course you are more on the kind of system hardware level security, but can you imagine that when we have quantum computers, that these problems also will arise, or that will be solved?
The problem with quantum computers is basically that the operations that we are performing on them, we don't, and it's inherent to how they work. We can't really observe this. So the only way how we can observe this is through measurements, and then they interact with a traditional computer, which then provides this information to a programmer again on an interfaceable level. This is very problematic because basically, in its essence, we are using a side channel there on the actual quantum computer to figure out what the quantum state is. So we are using side channels there already. I do have concerns that if we scale these computers up, we will not solve the problem of energy consumption at all, but this will cost a lot of energy because we are very inefficient in the way of actually interfacing with these computers, getting the information out, and this then requires huge amounts of redundancy so that you can get reliable results.
Physical qubits versus logical qubits.
Yes. I doubt that I will see the point where quantum computers will be outperforming our regular computers for reasonably sized tasks. For very small tasks, yeah, there are some demo examples, but not for reasonably sized tasks.
Thank you.
Yeah, there was one more question about reducing security standards with the current GDPR rules. I don't want to reduce security standards. I would like to add more security and then exploit these security guarantees to optimize more aggressively. The overall goal would be, if you optimize too far, it should never affect security. It should only affect the performance. And with that, you could optimize really, really very far, because the worst thing that can happen, it runs a bit slower again, a bit less efficient.
I'm looking at I've just a last question from my side.
Yeah.
Of course, this CPU undervolting is one way to save energy. Are you teaching this to all your students at TU Graz?
Well, we do have courses where students learn about this. I think primarily in the masters, but I think it also is briefly covered in one of our bachelor lectures. Yeah.
Do you know how much, if all this, is an estimate,
okay.
if all the students would use it, yeah, how much savings would be there already?
I think it's problematic because Intel disabled the interface on many machines after the Plundervault attack. And now, if I get a new laptop, I might not even be able to do that anymore. On AMD, you can still do this through the BIOS. On Intel, I'm not sure whether even on current gaming motherboards, you are still able to undervolt in this to the same extent. Yeah. I find it really sad because they could have left this feature enabled for some use cases, because it's not really relevant for anything but their SGX feature, and no one cares about that anyways.
I see no further questions, and it's also the undervolting is not available on my machine, for example. Okay, good. Now everybody.
Oh yeah.
Daniel, thank you very much. It was really, as usual, very exciting to listen to you. Thank you for all your insights. Please send us the slides, so we will put them online again. Thank you to the audience. What about Bitcoin miners?
Well, I mean, I'm not necessarily saying there are things that we should ban in our society in terms of technology that we can use, but this would be technology where I would say banning that would not be wrong. Yeah.
An own discussion about
Yes.
This has something to do with, the ethics of
yes, I do have ethical concerns about that. Yeah.
Exactly. I don't want to be shy not continuing this discussion here, but I guess it would explode our frame. of this lecture. Daniel, thank you very much again.
Thank you too.
Thank you to the audience. And yeah, we see each other next Monday. We continue with our sustainability in computer science lecture. And yeah, goodbye to everybody.